Good morning to all. Myself Paras Mehta from BSc Chemistry Honors final year. Today's our topic is carbohydrates. Introduction. One of the most classes of biomolecules is carbohydrates. These include compounds like sugar, starch, glycogen, dextrins, and gums. Although they are widely disturbed both in animal and plants kingdom, yet they are obtained mainly from plants. They are formed in plants by a process known as photosynthesis, make up about 70% of solid plants material. CO2 plus H2O, sunlight, chlorophyll, and CxH2O, Y carbohydrate बन जाएगा and oxygen separate out हो जाएगी. Carbohydrates play a vital role in our daily life. They provide us with three basic necessities of life: food, cloth in the form of starch, food, cloth, cotton, line, rayon, and essential cellulose, and shelter, wood in making house, furniture in almost cellulose. Classical definition: the name carbohydrate, meaning hydrate carbon, was originally given to a class of compound containing only carbon, hydrogen, and oxygen. The hydrogen and oxygen being present in the same ratio as in water, these compounds could therefore be represented by the general formula CxH2O. Limitation of all definition: the above definition could not survive long due to the following reasons. A number of compounds such as rhamnose C6H12O5, deoxyribose C5H10O4 are known, which are carbohydrate by their chemical behavior but cannot represent as hydrate of carbon. There are other substances like formaldehyde, HCHO, CH2O, and acetic acid, CH3COOH, which do not behave like carbohydrate but can be represented by the general formula CxH2O. Carbon is not known to form carbohydrates. Modern definition: carbohydrates are defined as polyhydroxyaldehyde or polyhydroxyketones or modern substances which gives these hydrolysis and contain at least one chiral carbon atom. It may be noted here that aldehydic and ketonic group in carbohydrates are not present as such but usually exist in combination with one of the hydroxyl group of the molecule in the form of hemiacetal and hemiketal respectively. Classification of carbohydrates. Carbohydrates are known as saccharides. These are classified into following three classes depending upon their behavior towards hydrolysis. Monosaccharides. These are the simplest carbohydrate which cannot be hydrolyzed to the similar molecule. Their general formula is CH2ON, where N is equal to 3 to 8. Oligosaccharides, Greek oligo mean a few. These are the carbohydrates which on hydrolysis give 2 to 10 molecules of monosaccharides. Depend upon the number of monosaccharides molecule actually obtained upon hydrolysis. They are further classified as di, tri, tetrasaccharides, etc. For example, disaccharides carbohydrate which upon hydrolysis gives two molecules of the same or different monosaccharides are called disaccharides. For example, sucrose, maltose, lactose, their soluble is C12H22O11. Disaccharides carbohydrate which on hydrolysis give three molecules of the same or different monosaccharides are called trisaccharides. For example, raffinose upon hydrolysis gives one molecule each of glucose, fructose, galactose. Their general formula is C18H32O16. Tetrasaccharides carbohydrates which upon hydrolysis give four molecules of the same or different monosaccharides are called tetrasaccharides. For example, starch rose upon hydrolysis gives one molecule of each glucose, fructose, and two molecules of galactose. Their journal formula is C24H42O21. Polysaccharides carbohydrate which upon hydrolysis gives a large number of monosaccharides molecules are called polysaccharides. The most commonly occurring polysaccharides are starch, cellulose, and glucose. Their journal formula is C6H10O5N, where N is 100 to 3000. Sugar and non-sugars. Carbohydrates are further classified as sugar and non-sugar. All the monosaccharides and oligosaccharides are crystalline solids soluble in water and sweet in taste. These are the collective called sugars. The polysaccharides on the other hand are amorphous solid and insoluble in water, tactile, and thus are called non-sugar. Reduced and non-reducing sugar or carbohydrates. Carbohydrates are classified as reducing and non-reducing sugars. All those carbohydrates which contain aldehydic or ketonic group in the hemiacetyl or hemiketal form and reduced tolerance reagent or Fleming solution are called reducing carbohydrates or sugar, while other which do not reduce these reagents are called non-reducing carbohydrates or sugar. All the monosaccharides, whether aldose or ketose, are reducing as sugars. Disaccharides such as sucrose, in which of the two monosaccharides units are linking through their reducing centers, aldehydic or ketonic group, are non-reducing, while other in which these group are in the acetyl hemiketal form are the reducing sugars. However, However, all polysaccharides, starch, cellulose, glucose, dextrine, etc., are non-reducing carbohydrates. Let us now briefly discuss each of one these classes of carbohydrates. Classification of monosaccharides. Monosaccharides. As stated above, monosaccharides are the simplest carbohydrate which cannot be hydrolyzed to smaller molecules. They contain 3 to 7 carbon atoms. There are about 20 monosaccharides which occur in nature. There are two types. Aldose. Monosaccharides contain an aldehyde CHO group are called aldose. Since the aldehyde group is monovalent, therefore it is always present at one end of the carbon chain at C1. Ketones. Monosaccharides contain a keto group are called ketosis. Since the keto group is divalent, it can be present anywhere along the carbon chain. However, in the all nature occurring ketosis, keto group is always present at the carbon atom next to the terminal carbon at C2. Aldosis and ketosis are further classified triasis, tetrosis, pentosis, isosis, haptosis, etc. according as their 3, 4, 5, 6, 7, etc. carbon atom respectively. The classification of monosaccharides in submarine table. Nomenclature. Monosaccharides are better known by the common name which is most case in suffix OSC. For example, ribose, glucose, fructose. Thus, IUPAC name of monosaccharides are seldom used. For example, the simplest aldose contain 3 carbon atoms CH2OH. CHOH is generally known by its common name glycerin aldehyde and seldom by its UPSC name. 2,3-dihydroxypropanol. Similarly, the simplest ketose CH2OH is better known by its common name dihydroxyacetone, seldom by its IUPAC name 1,3-dihydroxypropanone. However, monosaccharides contain more than 4 chiral carbon aldohaptose, aldoctose, etc. Are named by IUPAC system by using two or more prefix derived from the lower sugar. Thus, one chiral carbon glycerin 2, 3, 4, 3 ribo lexo 4 allo aldro gluco mono etc. The IUPAC name of sugar is then obtained by the giving the prefix denoting 4 chiral carbon. In the IUPAC system, ketones are named by the means of the suffix allos. Proceed by a prefix indicating the total number of carbon atom in the chain. The position of the keto group is usually indicated by a number. For example, fructose is a 2-hexalose. The configuration of a ketose is indicated by a prefix derived from the configuration of the chiral carbon atom in the corresponding aldose. For example, D-fructose is D-Arab in hexolose and D-subrose is called D-xylohexolose. Deoxy sugar. Sugar in which one or more hydroxy groups are replaced by hydrogen atom are called deoxy sugars. In the common system, deoxy sugars are named by adding the prefix deoxy along with the number of the carbon atoms from which the hydroxyl group has been replaced by the hydrogen to the common name of the aldose or the ketose. In a IPC system, deoxy sugar are named by adding two prefix to the name of aldose ketose containing the total number of carbon atom in the chain. The name begins with the prefix deoxy along with its locant followed by configurational prefix representing the system of chiral carbon atoms as shown above. Since most of the early work on the monosaccharides was carried out in the hexose, glucose, and aldohexose, fructose, ketohexose. Therefore, we will start our study of monosaccharides with the two representing compound. It may, however, be added here that what is true about glucose is also true about other aldohexose, and what is true about fructose is also true about other ketoses. The glucose, dextrose, or grape sugar C6H12O6. Glucose is the most widely distributed monosaccharides. It occurs free in the large quantity in ribes, grapes, and that is why it is called grape sugar. It is also occur in honey and the most of other sweet fruits such as mangoes, apple, peaches, pears, etc. It is also present in human body about 0.1% in the combined state. It is occur glucosides, disaccharides, and polysaccharides. Preparation of glucose. Laboratory preparation. In the laboratory, glucose is prepared by the hydrolysis of sucrose or cane sugar. C12H12O11 sucrose plus H2O. Reaction proceeding glucose plus fructose. Two compounds are formed C6H12O6. Manufactured sucrose is hydrolyzed by heating with diluted HCl or H2SO4 in 90% alcohol when a mixture of glucose and fructose is obtained. Glucose being almost insoluble in alcohol separate out on a cooling while fructose remain in the solution. On a chemical scale, glucose is prepared by the hydrolysis of starch with hot diluted mineral acid. The chief source of starch are rice and potatoes. C6H12O5N starch plus NH2O reaction procedure and we get glucose C6H12O6. After hydrolysis, the reaction mixture neutralized with the chalk CaCO3 and filtered. The filtrate is decolorized with animal charcoal and concentrated under reducing pressure with glucose crystalline out. Physical properties of glucose. Glucose is a crystalline white solid with melting point 419 Kelvin. It is highly soluble in water, perceptibly soluble in alcohol, insoluble in either. It is optically active and dextrorotatory and hence the name dextrose. It is about 3/4 as sweet as sucrose. Chemical properties of glucose. Glucose is a typical monosaccharide. It gives the reaction of both aldehydic and alcoholic group. In order to discuss these reactions, glucose may be simply represented as an open chain pentahydroxyaldehyde as shown below. CH2OH, CHOH, 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 CHO. Some important reaction of glucose are discussed below. Reaction of aldehyde group. Glucose gives the usually reaction of aldehydes. However, it does not respond to Skipp's reaction test. It also does not form addition compound with the saturated solution of sodium bisulfite. Reaction with hydrogen cyanide. Glucose form cyanohydrine with hydrogen cyanide. CH2OH CHOH4 CHO रिएक्शन हुई HCN के साथ एंड फॉर्म हुआ ग्लूकोज साइनोहाइड्रिन CH2OH CHOH4 CHOHCN reaction with hydroxylamine. With hydroxylamine, glucose gives glucose oxime CH2 OH, CH, 4 CHO. It's a formula of glucose. Plus NH4OH and the product form is glucose oxime CH2OH CHOH CH double bond NOH plus H2O. Reaction with phenyl hydrogen. Glucose react with 1 mole of phenyl hydrogen to form glucose phenyl hydrazone. Glucose plus H2N NHC6H5, it is a 1 mole of phenyl hydrogen, and then react with product we get product glucose phenyl hydrazone CH2OH CHOH4 CH double bond N NHC6H5 plus H2O. Osazone formation. Forever, if excess of phenyl hydrogen is used, the reaction proceeds further to yield a crystalline product called osazone, which contains 2 phenyl hydrogen residue per molecule of glucose, while the third molecule of the reagent is covered into aniline and ammonia. CHO, CHOH4, CH2OH. It's the formula of glucose. Plus 3 6 6 H5 NH NH2. अब की बार हमने इसको एक्सेस में दे दिया सी एच डबल बॉन्ड एन एच C6H5 सी डबल बॉन्ड एन एन H6H5 CHOH थ्राइस CH2OS ग्लूकोज ओजाजोन C6H5 NH2 NH3. It may be pointed out here that ozone formation is not only a characteristic reaction of reducing carbohydrates but is also given by the alpha hydroxyaldehyde and alpha hydroxyketone. In generally benzoin C6H5 CHOHCO C6H5. Further, during ozone formation, the stereochemistry about C2 chiral carbon of an aldose is destroyed without affecting the configuration of the rest of the molecule. Fletcher mechanism. Hamill Feature, who first prepared ozone, explained the mechanism of its formation as follows. The first mole reacts in a usually manner expecting an aldehyde. The second mole oxidizes the secondary alcohol group to the ketonic group, and the third mole reacts with the keto, thus generate to form ozone as shown below. Limitation of Fletcher mechanism. The mechanism suffers from the following defect. It does not explain why the phenyl hydrogen, which is strong reducing agent, act as an oxidizing agent in the second step of above mechanism. It does not explain why only the first two carbon atoms are involved in the ozone formation. Example, why do remaining hydroxyl group not get oxidized and react further with phenyl hydrogen? Modern mechanism. To overcome these objections, we proposed an alternative mechanism involving Amadori rearrangement. The phenyl hydrogen first form undergoes tautomerism to form a H-bonding six-membered intermediate. The intermediate subsequently loses a molecule of aniline to form an ketone and then react further with two molecules of C6H5 NH2, one at the C double bond O group and the other at the C double bond NH to give final ozone. The mechanism is supported by the observation that why phenyl hydrogen prepared from 15 and labeled phenyl hydrogen is treated with ordinary phenyl hydrogen. Unlabeled oxygen is formed with the elimination of labeled ammonia. The mechanism also does not explain why the reaction stops after the addition of two phenyl hydrogen residue. Hydrogen residue. Hydrogen residue. This has, however, been explained on the basis that oxygen is stabilized by chelation as shown below. The explanation is supported by the observation that unsymmetrically distributed hydrogen, which cannot yield oxygen capable of chelation, react further with aldose, forming alkozones in which ozones formation proceed along the whole carbon chain of the sugar. It may be noted that ozone formation is general reaction of all the monosaccharides and alpha hydroxyaldehyde and alpha hydroxyketones. An important point about the oxygen formation is that during its formation, configuration at C1 and C2 is destroyed. Eventually, any diastereomeric monosaccharides which differ from glucose only in the configuration at C2 should give the same oxygen. For example, monos which differ from glucose only in configuration at C2 give the same oxygen. In general, any pair of ampères which differ in the configuration at C2 gives the same oxygen. Oxygen are well defined bright yellow crystalline solid having defined shape. Therefore, oxygens are used for identification of monosaccharides and reducing disaccharides. Reduction. Glucose is rarely reduced catalytically or by sodium mercury amalgam and water to form hexahydric alcohol called glutamic and or s orbital. CH2OH, CHOH4, CHO, NiH2, glutamic or s orbital, CH2OH, CHOH4, CH2OH. However, on reduction with Hi in the presence of red phosphorus at 373 Kelvin, it gives a mixture of N-hexane and 2-iodohexane. Oxidation. Mild oxidation agents such as bromine water oxidize glucose to an monocarboxylic acid called gluconic acid. Strong oxidizing agents such as nitric acid, however, oxidize glucose to a dicarboxylic acid called gluconic acid and saccharic acid. The second carboxylic acid group being formed by the oxidation of the first primary alcoholic group, reducing nature. Due to ease with which CHO group in glucose is oxidized to COOH, glucose act as a reducing agent, thus reduce tolerance reagent molecule silver nitrate solution, failing solution alkaline CuSO4 solution containing Rochelle salt, and Benedict solution alkaline solution of cupric acetate containing citrate ion. Glucose plus tolerance reagent and then ammonium gluconate. Glucose plus Fleming or Benedict solution, sodium gluconate and red PPT of Cu2O. Reaction of the hydroxy group. Acetylation. Glucose reacts with acetic anhydride to form glucose pentaacetate. Glucose plus acetic anhydride CH3CO twice O. Pyridine. In the presence of pyridine, the reaction proceeds. Glucose pentaacetate formed. CH3CO, CH2, CHO, CO, CH3, 4, CHO, and CH3COH also formed. Formation of glycosides. Glucose react with methanol in the presence of dry HCl gas to form to mixture of alpha and beta methylene glucosides. Glucose plus CH3OH in the presence of dry HCl reaction proceed and alpha and beta methyl glucosides formed C6H11O5O CH3H2O. Formation of glycostates. When treated with slack lime CaOH twice, glucose forms soluble calcium glucostate. Glycostate. Glucostate. Glucose plus CaOH twice, calcium glucosate soluble बताइए C6H12O6 CaO plus H2O. Other reaction. Action of acids. Dilute acid have no effect. However, if glucose or any carbonate is treated with concentrated hydrochloric acid, it gives 5-hydroxymethyl furanol, which is further converted by hot hydrochloric acid to levulinic acid. The 5-hydroxymethyl furanol formed above gives violet coloration when treated with alpha naphthol. This reaction therefore forms the base of Molish test for carbohydrates. Action of alkalines. Lobry de Bruyn van Eckenstein rearrangement. When glucose is treated with a concentrated solution of an alkaline, it first it first turns yellow, then brown, and finally a brown resinous mass is obtained. However, when treated with a dilute solution of an alkali, it forms equilibrium mixture of glucose, fructose, and mannose. The reaction is called Lobry-de van Eckstein rearrangement. It involves the formation of 1,2-indiol as a transient intermediate in which the clarity of C2 is destroyed due to the formation of carbon-carbon double bond. This unstable intermediate then change into a mixture of three monosaccharides as given below. The same equilibrium mixture is obtained even if one starts with mannose and fructose. It is probably because of this isomerism that fructose reduces tolerance in Fleming solution even though it does not have CHO group. Fermentation. The enzymes present in yeast readily brings out the fermentation of glucose of ethyl alcohol C6H12O6 Jimesh ethyl alcohol C2H5OH plus CO2. Open chain structure of glucose. Open chain structure. The open chain structure of glucose follows the from the discussion. Molecular formula. The molecular formula of the glucose is determined from analytic data and molecular weight determination is C6H12O6. Glucose react with HCN to form cyanohydrin with hydroxyamine to form oxime with equimolar amounts of phenylhydrazine to form phenylhydrazone. All these reactions suggest the presence of carbon group in the glucose. C6H12 react with HCN cyanohydrin react with NH2OH oxime. Glucose react with C6H5NH NH2 phenylhydrazone. On mild oxidation with bromine water, glucose gives gluconic acid and acid contain the same number of carbon atom as glucose. Glucose react with bromine water gives gluconic acid C5H11O5COOH. These reactions suggest the while group present in glucose must be an aldehyde group. Presence of 5-hydroxyl group. When treated with acetyl chloride or acetic anhydride, glucose form a pentacetate. Thus, glucose contains 5-hydroxyl group. Further, since glucose does not lose water readily, each hydroxyl group must be present on different carbon. The presence of 5 hydroxyl group and one aldehyde group in glucose is further confirmed by the fact that glucose on reduction with sodium amalgam and water gives s orbital which form a hexaacetate on treated with acetic anhydride. Glucose react with sodium amalgam gives s orbital and after that give hexaacetate. Presence of one primary alcoholic group. Glucose on oxidation with nitric acid give glucaric acid and a or dicarboxylic acid containing the same number of carbon atom as glucose. One of the carboxylic group in a glucaric acid must have been produced by the oxidation of the aldehyde group and the other must have been obtained by the oxidation of a primary alcohol group. Glucose react with HNO3 gives glucoric acid. This is one of the 5 groups present in the glucose must be a primary alcohol group. Presence of a straight change of a carbon atom. Glucose and reduction with Hi and red phosphorus at 73 degree Kelvin temperature give a mixture of N-hexane and 2-iodohexane that indicate that 6 carbon atoms in glucose are arranged in a straight chain. Glucose react with Hi red phosphorus gives N-hexane plus 2-iodohexane. This is further confirmed by the fact that glucose cyanohydrin on hydrolysis and subsequent reduction with Hi red phosphorus gives one heptanoic acid. Glucose react with HCN give glucose cyanohydrin. After react with H positive hydrolysis C5H11O5CHOSCOH and after react with HF red phosphorus gives one heptanoic acid. From the above discussion, it follows that glucose contains one aldehyde group, 5 hydroxy group, out of which one is primary, a straight chain of 6 carbon atom. Further, since the aldehyde group is monovalent, it must be present at the chain. Keeping in this view fact and the tetravalency of carbon, the following open chain structure is this. The above structure of glucose is confirmed by its oxidation with HiO4 malaprate reagent, which conforms 5 moles of HiO4 and produce 1 mole of formaldehyde and 5 moles of formic acid. Glucose react with HiO4 and after that third mole, fourth mole and form formaldehyde plus formic acid. Configuration of deepose glucose. The open chain structure of glucose contain 4 chiral atoms. Therefore, it should be exist in 2 4 is 2 to the power 4 is equal to 16 optical active stereoisomeric form. All those 16 stereoisomers are known and exist as 8 pairs of anti enantiomers and 8 belonging to D series and 8 belonging to L series. This in fact corresponds to D and N form of allose, altrose, glucose, idose, etc. Out of these 16 stereoisomers, one is D positive glucose and there is its enantiomers, L negative glucose, the rest 14 being diisomers of D positive glucose. However, there would be no mesoform since two ends of molecules are dissimilar. The absolute configuration of D positive was established by the Ambil feature in 1891, who was awarded by the Nobel Prize in 1902 for his work. For this work, the detail of this produce is, however, discussed in section 20 under experimental proof of absolute configuration of aldose. Thank you very much for listening. Thank you.